Hey guys, Mr. Betts here. I want to talk about another convergence test that we can use to see if a series converges or diverges. This is actually a test that I have used kind of informally in the past to show that the harmonic series diverges. And the idea is this. If we have a series that looks like this, this series is going to behave in the long run like n over n squared, or the harmonic series 1 over n. So this series is going to behave like the series, this series 1 over n, and we know that this series diverges. So based on the fact that it's going to behave like that when n gets really big, we would suspect probably then that this series would also diverge. Well, if we write out the first few terms in each of these, we're going to get, when n equals 1, we're going to get 2 over 1. When n is 2, we're going to get 3 over 4. When n is 3, we're going to get 4 over 9, 5 over 16, and so on. That keeps going. And then with the 1 over n series, we're going to get 1 over 1 plus 1 over 2 plus 1 over 3 plus 1 over 4, and so on. And if I rewrite the bottom series so that we have common denominators, this is 2 over 4, this is, let's see, 3 over 9, and 4 over 16. And you will notice that term by term, each term in this series is bigger than the corresponding term in this series. So we know that this sum approaches infinity. And we know the terms in this series are each bigger than the corresponding terms in this series. So it would make sense then to say that this series will also approach infinity because it is bigger term by term. So if we add enough terms in this series, we can make this sum as big as we want, and the corresponding sum in this series is always going to be bigger. So by comparison, each term in the first series, let me clear this so I can talk about it a little more. So each term in this series right here is going to be bigger than each term in the harmonic series. So what we really want to show is that as n is getting bigger, we want to be able to say that that is bigger than that. And indeed, we can say that this is compared to n over n squared. Since the numerator here is bigger, we know that that's going to be bigger. So denominator is the same. Numerator here is bigger, makes that term bigger. And this is equal to 1 over n. So no matter what n value we choose, the term in this series is going to be bigger than the term in the harmonic series that corresponds to it. So this idea is called the direct comparison test. We could also use this idea if we have a series that is smaller than a series that we know converges. Then we can use this direct comparison test to say that the series converges. It is not real powerful because if I change this just a little bit and make this a -1 instead of a +1, now all of the terms in this are smaller than the terms in a series that we know diverges. And even though this sum is going to approach infinity, this one's smaller, and we don't know if it's also going to approach infinity, or we might have a series that is going to converge. It actually turns out that even though the terms are smaller, it is still going to approach infinity, but we can't know that just based on the fact that the terms are smaller than a divergent series. So it's only useful if we can show that a series is term by term bigger than a divergent series, or term by term smaller than a convergent series. So that gives us the direct comparison test. And there's really two cases. There's a lot of stuff going on here, but essentially what we have is what's called a comparison series. So a comparison series is going to be a series that we already know whether it converges or diverges. And we have a series that is, I'm going to call it a test series. So we want to test whether or not this series converges or diverges. If the terms in the convergent series are bigger than the terms in the test series, so we have this relationship here, then the test series is going to have to converge also. Okay, so put another way, if the terms in the test series are smaller than the terms in the comparison series and the comparison series converges, then the test series does also. Now, there's a little bit of extra stuff here that says for all values of n greater than or equal to some n, big N, which is an integer. Basically, what that's saying is we could have a series that is, I don't know, smaller than the harmonic series for a certain period of time. So this would be smaller than the harmonic series for one. This is not a great example. But then all of a sudden now it's going to be bigger later on, or smaller later on, depending on which version we're using. The big idea here is if we can compare the terms as n gets really big, that's what we're looking at. So the other case is if the comparison series diverges and the terms in the test series are bigger, then the test series itself will also diverge. These are 2 of 4 possible cases. The other 2 cases where a series is smaller than a divergent comparison series, or a series is bigger than a convergent comparison series, then we don't know what's going to happen. So we do need to be careful that we are not trying to use the direct comparison test when it really shouldn't be used. So let's take a look at a few examples of series that we might compare. I want you to notice that on the right side of each one of these is a series that we can actually tell if it converges or diverges using the P-series test. So even like this one is the same thing as 1 over n. This thing is 1 over n to the 1/2. So on the right side, those are going to be our comparison series. And our left side, those are going to be our test series. So in the first one, if we increase the denominator by 1, then overall, if we're making the denominator bigger, we're making the whole thing smaller. So we're going to get a less than here. Likewise, in this one, if we decrease the denominator, then we're going to make the whole thing bigger. In this one here, we're decreasing the numerator, which is going to make that smaller. And at the same time, we're increasing the denominator. Now, you might think, well, n could be negative, which would actually decrease it. But keep in mind that n is approaching infinity. So we're looking at what happens as n approaches infinity. So that's going to be a positive number. So both of those things are going to decrease it. So that's going to be less than n squared over n cubed. The last one, essentially, we have n squared on the bottom. We want to compare the tops. And as n gets really big, the natural log of n is going to be bigger than 1. So that's going to be greater than. Now, I will point out that for some values of n, the natural log of n is less than 1. However, since n is approaching infinity, this is going to be bigger than 1, which makes natural log of n over n squared bigger than 1 over n squared.